Welcome everyone. This lecture of dynamics of the lithosphere is about local isostasy. Several models of isostatic compensations have been proposed, and they basically fall in two categories. One called the local isostatic models and the other called regional isostatic models. So the local isostatic models are namely the Airy and Pratt models, and the regional isostatic models are the elastic flexure models. So you see two sketches here. This is supposed to represent local isostatic. So you see a load here and a plate below a load which is completely deformed. In the regional case, there is a load. It's supposedly a similar load as this one, but below there is a plate which is bent and basically exhibits some rigidity. So the topic of this lecture is not regional isostasy. This topic we will discuss in the next lecture. Today we focus on local isostasy. Now the question you may ask is, what is common between a floating iceberg, a floating cargo ship, a giant toy duck floating on the lake, and a mountain belt such as the Alps here? So that's a cross section of the Alps over 80 kilometer thickness and a topographic profile here on the top. There is indeed something common. It may not be obvious, but all of these systems are supposed to follow the Archimedes principle. So this is Archimedes, such as represented or painted by Domenico Fetti in 1620. And what states Archimedes is that any object which is totally or partially immersed in a fluid or liquid is buoyed up by a force equal to the weight of the fluid displaced by the object. So let's have a look in more detail. Here is a very schematic diagram showing you an item immersed or partially immersed in a fluid. So you have the surface of a fluid here. The item is this bar, and it's cropping out at the surface of the fluid. So it's a bit like the picture of the iceberg. That's the tip of the iceberg and the root of the iceberg. You have the axis coordinate y, which is 0 at the surface, and increasing downwards. The gravity is also acting downwards. So the surrounding fluid is all around the place, and the floating object is restricted to this area. The local isostatic models will rely mainly on two principles, and the first principle is the simplified force balance. So if we keep focused on this diagram here, we will see two forces which are of two different kinds. The first force is the body force. So the body force is the force which is acting over the whole dense object here, over the entire volume of the object. So it's proportional to the gravity, the density of the object, of course the depth extent y, and the section of the object. So y times delta A makes a volume. So you have density times acceleration of gravity times the volume of the object. The second force here acting upward is sigma yy times delta A. So that's a surface force. It's a reaction to the immersion in the fluid. So the question you may always ask yourself was, what is the unit of the force? This you should always recall, that force is proportional to mass times acceleration. and that's unit Newton. And how to relate the stress or a pressure to a force? It is via the area, here delta A. So stress is a force per unit surface. So stress as unit Pascal, it is Newton per square meter. Now we want to use the principle of force balance or static equilibrium, and we make the sum of the surface force is equal to the sum of the body force. We have one surface force and one body force. So we have basically sigma yy delta A is equal to rho gy delta A. Now delta A appears on both sides of the equation, so we can simplify this by sigma yy is equal to rho gy. This comes from static equilibrium. That's the balance of the surface force and the body force. Now we need a second ingredient to build the local isostatic model, and this is called the compensation principle. So what does it mean? A compensation principle invokes a compensation depth. It is a depth at which the weight exerted by adjacent columns of rock will equate themselves. This will set the isostatic compensation. So it basically means that if you have two lithospheric or crustal columns of different thicknesses which are adjacent to each other, there should be a depth somewhere down in the earth where the pressure below these two columns is equal. So that's the second ingredient. We have the static equilibrium and the isostatic compensation. Also, one thing to keep in mind is that there is no feeling of lithosphere resistance in the local isostatic model. So in fact, the lithospheres assume stress-free and the rheology doesn't matter. So to make it very sketchy, you can represent a mountain belt this way. So you would have a continental margin here, lowlands, highlands, and below you may now know that there is a variation of the Moho depth below the system, and these are smooth variations. In the case of a local isostatic model, we would assume that each of these that the crust can be discretized into blocks that slide past each other without any resistance. So there is no resistance of the underlying mantle. But we will discuss this in more details in the lecture on flexure. So let's go back to the mid-19th century. So we are basically 50 years before the acceptance of the tectonic nap theory, in a way, or the discovery of tectonic naps. 110 years before the acceptance of the plate tectonic theory, and 130 years before modern exploration geophysics. Below is a current cross-section of the Himalayas, and so if we go back to the mid-19th century, we basically have no knowledge of the internal structure. We don't know about the naps, we don't know about the collision between the plates, the main interplate structure, and the intracontinental deformation associated to it. Most of the information is actually coming from field geology that mainly resides on observation made at the surface and try to be extrapolated to depth, and field geodesy, which also uses measurements made at the surface. in the 19th century, geodetic campaigns were aiming at measuring the deflection of plumb lines in the India-Himalaya collision zone. So what does it mean? It's basically, the idea was that the mountains are high in the Himalayas, so the mean altitude of the plateau may be 5 kilometers. So they represent mass excess. And if you would have local mass excess, you would basically impact locally the gravity field. So you would attract object by the mass excess. So if you would walk with a plumb line, your plumb line should be deflected towards the mass excess represented by the mountain belts. So that's where the model of Pratt comes into play. So John Henry Pratt was appointed as chaplain to the Bishop of Calcutta, and he wrote an article in 1854 about the attraction of the Himalayan mountains and the plumb line in India. So what happened is that the plumb lines, they were not deflected as expected. When the campaign was made, they observed deflection of the plumb lines from India towards Himalaya was tiny with regard to the expectation. So there was a need to explain this. Why are the plumb lines not deflected towards Himalaya? And this is where the model of Pratt comes into play. So he had to formulate a hypothesis. And his hypothesis is that crustal columns that reach a uniform depth have different densities. So let's have a look at it this way. So you would have a crustal blocks here, and you see that all these crustal blocks have a flat base. They all have the same base. They have a different topography. So this would be a reference block. The thicker block, the higher block, would be lighter, would have a lower density, and the thinner block, which here is accommodating a basin, would be denser. So now you see another sketch. You have blue blocks. These are normal thickness crusts, thickness H. A red block, which is a crust with excess thickness delta H. And both of these blocks have different density, rho C2 and rho C1. Below is a mantle of density rho M. So let's use static equilibrium here. H times rho C1, so this is the load exerted by column, blue column, is equal to the load of the red column. So H times rho C2 plus delta H times rho C2. Now one can solve for the density of the red column to try to find what is the density anomaly. So let's do that. Solve for rho C2. You obtain H times rho C1 divided by H plus delta H. You set values now. So let's assume that rho C1, the crust of normal thickness, has a density of 2,700 kilogram per meter cube, a thickness of 30 kilometer, and let's assume that the height of the plateau, the mean height, would be 5 kilometers. Now you obtain this number. Rho C2 is 2,310 kilogram per meter cube. So in this case, this would be a very low value. If you would apply this to the Himalayas, it would mean that the Himalayan block, which has the topography, has an extremely low density. So 2,310, it's a density which is even lower than that of serpentinite, which is 2,600 kilogram per meter cube. So this is not very realistic. It's a bit too low. So here comes the model of Airy. So Airy was professor of astronomy at Cambridge and astronomer. And he wrote an article in 1855 on the computation of the effect of attraction of mountain masses. So you see a little sketch here, that would be the Earth, and you see a bump here, it would be a mountain plateau. And what's new now is that below there is a deflection here. There is a root below the mountain, so it's not a flat base. And now that may start to recall you this image of the iceberg with the root. So that's a completely different picture than the Pratt model. So now we go back to this type of sketch. You see a crust of normal thickness. The adjacent block here has a topography, and now it features a root which is anchored in the mantle. So next to this material is directly mantle. Another feature is that in the region of thin crust, you would have a basin here at the top, but below you would have an anti-root which compensates the thinning of the crust. So in this model, the density does not vary between one block and the adjacent blocks. It's rather the crustal thickness that varies between the different domains. So let's make a little example again. Now we have the blue crust, thickness h and density rho c. The red crustal domain with a plateau of height delta h has a density rho c, like the blue block, but it has a root of thickness hm. So let's equate the pressure exerted by the blocks. So now we have the blue/green column. It has a thickness of h times rho c, that's the contribution from this block. And if you want to equate it to the pressure exerted at this block that has an extra root, we need to take into account this bit here, which has a thickness of hm and has a density of rho m. This is a mantle part. This is why it's blue and green column. It's this whole part here. And this pressure should be equal to the pressure exerted by this block here, which has a total thickness of delta h plus hm, and it's multiplied by the density of the crust, rho c. Having this, it's possible to solve for the root thickness, hm. It's usually the information that we don't know because we cannot observe it. So let's solve for hm, and one obtains rho c delta h divided by rho m minus rho c. Fairly simple formula. And now let's insert numbers in there. So we assume again that the crust density is 2,700 kilogram per meter cube, that the mantle density now, we need to use a mantle density. We set it to 3,300 kilogram per meter cube. Delta H is still 5 kilometers. And one will obtain 22 kilometers if you plug in these numbers. So 22 kilometers, if we assume that the thickness of the adjacent block is 30 kilometers, it's a normal crust thickness, you can compute the total crustal thickness of the red block representing the Himalayas here. You would have 22 plus 30 plus 5. And this would give you a thickness of about 60 kilometers. So that's rather an interesting estimate. If you remember, that's a sample from last week's course, coming from a global map of crustal thickness. The thickness of the crust below the Himalayas should be around 70 or more kilometers. So we are getting closer to these numbers. It's yet a little bit low, but it's not a bad estimate, and it's also rather an agreement with current exploration geophysical tools. So this is an example of a recent study on receiver function. So it's a seismological exploration tool that shows you the transition between the sub-Himalaya and the Himalayan plateau to the right, and the dark points here are showing you the position of the moho. So you see that in the Indian side it's about 40 kilometers, while it deepens to 60 kilometers here towards the Himalayan plateau. So just to summarize, there are two main local isostatic model, the Airy model. So the Airy model assumes that crustal columns which are adjacent have different thicknesses, and the Pratt model that assumes that adjacent columns have different densities. In both cases, one can express pressure at compensation depth and equate the pressure of two adjacent columns to solve for one of the parameters. So in the case of Airy, you would have this set of parameters, h, small h, large h, delta h here, and same density between the crust and the mantle part here. While in the case of Pratt, you would not involve density of the mantle, but you would involve a density difference between the two crustal blocks. So one example here is that you could solve for the root thickness, while in this case you can solve for the density difference between blocks. Of course, you can always fix this parameter and solve for another one. So this you will use in the exercises, and the exercises is pretty interesting because you would get to use topography from synthetic orogens and topography of synthetic rifts, and your aim will be to try to predict the morphology of the underlying moho. And more than this, you will also use data. So I'll give you a profile, a topographic profile across India and Himalaya and further up, and you will predict the thickness of the moho using the local isostatic models. So now to discuss a little bit, the local isostatic models, they work, but they only work to some extent. they are very simple, and since there is no notion of resistance, in particular notion of the resistance of the underlying mantle, you can get very wiggly patterns. It's basically assuming that the mantle has no resistance, you will get very local compensation. What does it mean? It means that the mantle deformation, if you move the blocks up and down, the deformation which is induced is accommodated actually locally. It's not transformed laterally. So the deformation acting or taking place below one column here will not affect the neighbors. You will not feel the neighbors. So this is the main limitation of the local isostatic models. And due to this, the local isostatic models, they fail to predict Mwp depths under volcanic islands or ice caps. So that's a nice section into a volcanic island. So you see a map of seismic velocity in a volcanic island. And what can be seen from this, you basically see the bathymetry here. There are some sedimentary or clastic deposits here on the sides. And you see the Mwp. So the Mwp is deflected below the load, but it's deflected also away from the load. So it means that the mantle basically has some resistance, which cannot be neglected in this case. So we need to go further than simply local isostatic models. That's what we will do in the next lecture. So as a summary, we've started discussing isostasy. Now you should be familiar with the principle of local isostasy. Next, we'll move on to regional isostasy. And as an introduction to regional isostasy, we will first discuss strain and elasticity. So this will make the bridge towards rheology of plates. Thanks for your attention.